Hello everybody, and welcome back to another episode of Bowmath. Hope you're all having a lovely day today, be it morning, afternoon, or evening. Or maybe it's the wee hours of the morning and you're getting your Bowmath fix. In either case, we are doing a checkpoint today where we are going to be covering everything from lessons 23 to 34. So that's all the fraction stuff we've done so far. And we've covered, a good range of stuff, and, I figured today's an appropriate time to do a checkpoint. So if you haven't yet, go back and do some review on these lessons to make sure that you're comfortable with the topics, because this is going to be a good test of your skill, and it would be kind of a waste for you to not try these out yourself. So assuming that you've watched the videos, you're feeling good with the topics, you've done some of the practice, give this a go, give it a good honest shot, and once you've done that, we will go through it together. So assuming you've done that, let's get cracking. Alright, so question 1 starts off with some addition and subtraction problems. It says calculate the following. Express your answer as a mixed number when applicable. Alright, so for part A, we've got 3/5 plus 4/5 minus 2/3 plus 0.2. Alright, so right off the bat, we can combine this 3/5 and 4/5 because that's a common denominator. So that's going to be 7/5. And then we still have this minus 2/3 and 0.2 to deal with. Now, this 0.2 we're going to want to express as a fraction because we're going to be ultimately combining these fractions. So we can already go and write 0.2 as 2 out of 10. Alright, doing so, 2 out of 10 can actually be simplified to a fraction of 1/5, which is nice because we already have a fraction out of 5 over here. So doing that, we're going to get 7/5 minus 2/3 plus 1/5, and we can combine these fractions out of a fifth to get 8/5. Alright, we've put it off long enough now. We have two different denominators, so we need to make a common denominator. Since 5 and 3 are co-prime with each other, their common denominator will be their product. Right, so our common denominator is going to be 15, 5 times 3. So we're going to multiply this fraction by 3 each, and we're going to multiply this fraction by 5 in the numerator and denominator each. What that's going to get us is 24 out of 15 minus 10 out of 15. 24 minus 10 is 14, so our final answer for this problem is 14/15. And if you'd like some more practice or you weren't sure how to do that one, check out episode 27 of this series. Alright, part B, we have negative 3 and 2/5 plus 9 and 1/3 minus 47 over 15. Okay, so to do this one, we have two mixed numbers and an improper fraction. So I'm going to use the method where we convert these mixed numbers into improper fractions, and then we'll go from there. So to make this negative 3 and 2/5 into an improper fraction, so we do 3 times 5, which is 15, plus 2, which is 17, but we can't forget our negatives, so we get negative 17 over 5. Similarly over here, we do 9 times 3, which is 27, plus 1, which is going to be 28, so we've got 28 over 3. And then over here, we have minus 47 over 15. Well, once again, we have a denominator of a 5 and a 3. And their common denominator, as we saw at part A, is going to be 15, which we already have here, so that's nice. What we need to do is just multiply this fraction's numerator and denominator by 3, because that'll give us the denominator of 15 we want. And then similarly over here, multiply it by 5. Doing that, we're going to get negative 17 times 3, which is negative 51 over 15, plus 28 times 5 is 140 over 15. Minus 47 over 15. Alright, combining these, I might combine the negatives first. So we'll have 140 over 15. And then we have negative 51 minus 47. So 51 and 47 is 98, and these are both negatives. So this becomes minus 98 over 15. 140 minus 98 is 42, and we get over 15. And this can be simplified because if you notice, both 42 and 15 are divisible by 3. So dividing those each by 3, we get 14 over 5. But this asks us to express our answer as a mixed number, right? So to make this a mixed number, we're going to have to do 14 divided by 5. 5 goes into 14 twice. Subtract off that 2 times 10, which is 4. That's our remainder. So we get 2 as the whole number part, and then our remainder is 4 out of the 5 we're dividing this improper fraction by. Okay, so 2 and 4/5 will be our final answer here. And if you're struggling with that one, make sure to check out episode 30 of this series, and that might help you out a bit. All right, so question 2 asks us to perform the following conversions. So we know from the videos that basically decimals, improper fractions, and mixed numbers can all be converted between each other quite freely, so this is just testing that. So for part A, we have convert 1.88 into an improper fraction. Okay, so to make this an improper fraction, we start by just writing the number in the numerator without any decimal, right? So we got 1.88 here. And then the decimal was slid over twice. So that means we're going to be dividing by 1 followed by 2 zeros, or 100, right? So we have 188 over 100. But now what we want to do is actually simplify this. So to simplify this optimally, we can basically just divide by their greatest common factor. So to find that, let's do some prime factorization. So 88, that's definitely a multiple of 2. And 94 is going to be half of that, right? So 2 times 94. And 47 should be prime. So we're looking at 188 is 2 times 2 times 47. And 100's prime factorization is going to be 2 times 2 times 5 times 5. So it looks like their greatest common factor is this 2 times 2, or 4. So we can divide both of these by 4. So the top, we're going to get 47. And the bottom, 100 divided by 4, is 25. So it looks like 47 over 25 is going to be our answer for part A. That type of conversion was covered in episode 28 of the series. For part B, we're looking at converting 5 3/8 into an improper fraction. Now, the fast way of doing this is to just multiply 5 by 8 and then add the 3. But I'll also just go for the long method here, just so that we can say we've done it once. It's been a little while. So what we do is we say, okay, this is 5 plus 3/8. And then this 5, we can make a fraction out of 1. But now that we have a denominator of 1 and a denominator of 8, we can actually make a common denominator by multiplying the numerator and denominator of this 5 over 1 by 8 each. And then what that gives us is 40 over 8 plus 3 over 8, which is 43/8. And again, the fast way of doing this is just to do 5 times 8, which is 40, plus the 3, which gives us 43/8. But either way, that is our answer. And I talked about this type of conversion in detail in episode 29 of the series. Let's look at part C. We want to convert 10 over 99 into a decimal. So the way we did this was we just did long division. So we have 10 divided by 99. 99 can't go into 10, so we'll put a 0 here. And then we have to put a decimal to actually expand the amount of digits we have to work with. So 99 goes into 100 once. Subtract that off, and we get a 1. And then we bring down a 0. 99 can't go into 10, so we put a 0 here. And then we bring down another carry of a 0, and it goes in once. Subtract it off, we're back at 1. And notice, it looks like we're just going to get the same pattern, right? We bring down a 0, we get a 0, it can't go in, so we get a 0. And then we'll bring down another 0, and 99 will go in once. So it looks like it's going to be basically this pattern of the 1 and 0 repeating over and over again. So we can then say that our final answer is 0.101 with the 0, 1 repeating over and over again. And that type of conversion was covered in episode 25 of the series. All right, part D says convert 7.24 into a mixed number. So we have 7.24 and a mixed number that had a whole number part and a fraction part, right? So the whole number part is just 7. And then this 0.24 we can write as basically 24 over 100, right? So we're just looking at the decimal piece as a fraction, which can be considered as this 24, right? The 24 there without the decimal, and then it was slid over 2 times, so that's dividing by 100 there. But 24 over 100 can be simplified. These are both divisible by 4. So we get 7 plus, and then 24 divided by 4 is 6. 100 divided by 4 is 25. So 7 plus 6 over 25, which written as a mixed number is just 7 and 6/25. And that was covered in episode 28 of the series. Let's look at part E. Without using long division, convert 24,321 over 5 into a decimal. Okay, so for this one, we need to recall the cool little mental math trick we did, because we're not allowed to use long division here, so we have to use a different method. So we have to use the mental math trick, which was to double the number and then shift the decimal over by 1. So doubling this, we get 48 642, right? All I'm doing is doubling all these digits. We don't have any carries to worry about, so that's a nice quick doubling. And then we slide the decimal over by 1. And if you want to know why that works, check out episode 29.5 of the series where we do kind of a fun little demonstration about this mental math technique. And then for the last part, we need to convert negative 5,000 over 3 into a mixed number. So we're going to do that by doing 5,000 divided by 3, and we will take the whole part to be our mixed number piece and the remainder to be kind of the fraction component, and we'll just worry about the negative afterwards. So 3 goes into 5 once, subtract off of 3, we get 2, bring down the 0, we get 20. 3 goes into 26 times. 6 times 3 is 18, subtract that off, we get 2. And we're back at 20. So we're just going to be kind of repeating this 6 until we get to the end here. And now we stop at our remainder of 2. So what we end up getting is 1,666. And then our remainder of 2 is going to be the numerator over our original denominator of 3. And this is all negative. So this is going to be the mixed number. And that was also covered in episode 28 of the series. Question 3 asks us to order the lists of numbers. So we've got a list of numbers and we have to put them in order. So for part 1, we can split up the negatives and the positives, right? Because we've got some negative numbers, we've got some positive numbers. So we know that negatives are always less than positives, so we can kind of focus on these two situations and then order them from there. So our negatives are negative 3/4, negative 3/13, and negative 0.75. All right, so let's look at these first. So the negative 3/4 and the negative 3/13, they have the same numerator, right? Which means that we can compare them based on their denominator. And we know that the larger the denominator, the smaller the fraction. So that means this 3/13, since it has a bigger denominator, has basically a smaller size. But since these are negative, that means their size goes to the left of 0. And since the way we order numbers is their position on the number line, negative 3/13 actually comes more to the right than negative 3/4 because it's closer to 0. So we would see then that negative 3/13 is actually greater than negative 3/4. But now we just need to look at the negative 0.75. But if you recall, 0.75 is just 3/4 actually, right? So we actually can just write negative 0.75 equals negative 3/4 in this ordering here. Basically, this is a repeat element. It's just written in a different way. All right, so now we can look at the positive parts. So in the positive side, we've got 1.2, 7/8, and then 701 over 21. Now, to compare these numbers, well, we can just look at kind of what whole numbers they are around, because 7/8, that has a smaller numerator than a denominator, so 7/8 is less than 1. So that automatically means it's going to be smaller than 1.2. And 701 over 21, this is a massive numerator compared to that denominator, right? I mean, 21 times 2 is 42, right? And this is even bigger than that. So this number right here is definitely bigger than 2, which means it's definitely bigger than 1.2, and it's definitely bigger than 7/8. So just by looking at kind of what whole numbers these are bigger than or less than, we can order these pretty readily. So 7/8 being less than 1 is less than 1.2, and 1.2 being less than 2 is definitely less than 701 over 21, which is much larger than 2, right? This is even bigger than something like 5 or even 10. So we have our ordering of the positives, and since negatives are always less than positives, we can put another inequality right there, and we have ordered our first list of numbers. The second list of numbers, we're not so lucky with having some negatives and some positives, they're just all positives. So we're going to have to do a lot more comparing here. So we've got 3 and 1/6. We have 17 over 6, we've got 3, we've got 17 over 4, and we've got 3.2. So at the start, it's kind of nice that we can basically note that, okay, we have 3 and 1/6, we have a 3, and we have a 3.2. So these are all in terms of kind of, we can see what whole numbers they're between. These are between 3 and 4. Maybe we should convert 17 over 6 and 17 over 4 into mixed numbers so that we can basically figure out what whole number they're actually between. So let's go ahead and do that. 17 over 6, if we do 17 divided by 6, we see we get 2 with a remainder of 5. So that means 17 over 6 is the same thing as 2 and 5/6. And 17/4, if we do 17 divided by 4, what we end up getting is 4 1/4. So now that we have that, it actually will help us order them easier, right? Because 2 and 5 6, that's less than 3. And since all of these are 3 or larger, this is going to be our smallest element. So 17 over 6 is definitely most to the left on the number line. And then 4 1/4, well, that's the only one that's bigger than 4, right? That whole number tells us that we're bigger than 4. The rest are in the 3s, so this is going to be our largest element of 17 quarters right there. So now what we have to do is we have to compare the 3, 3 1/6, and 3.2. Well, 3 is definitely the next smallest one because it has no decimal part to it, right? Whereas these, they definitely go a little bit more than 3 because of that fraction and because of that 0.2 there. So now we just need to basically compare the 1/6 of this 3 1/6 to the 0.2 of this 3.2. So it might be helpful to write 3.2 as a mixed number. So we know that 0.2 is the same as 2 over 10, which can be simplified to 1 over 5. So 3.2 is the same as 3 1/5. So now essentially, we're comparing the 1/6 with the 1/5. And since they have the same numerator, we can just compare the denominators. This has a smaller denominator, which means this is the bigger fraction. So that means 3.2 is going to be larger than 3 1/6. But since it's less than 4, which 17/4 is bigger than, it's going to be in second place here. So this looks like our ordering for this set of numbers here. And if you want a video to get more comfortable with this topic, check out episode 32 of the series. It's February 3rd, 2013, and you live in Canada. You have 13 quarters, 7 dimes, and 89 pennies. How much money do you have in total? Use fractions to find your answer. So the only reason I put this date here is because on February 14th, 2013, pennies went out of circulation in Canada, so you stopped being able to use them at stores and whatnot. So we have 13 quarters. So recall that 13 quarters, literally in the name, that can be expressed as a fraction of 13 over 4. 7 dimes, right? So 1 dime is a tenth of a dollar, so 7 of them, that's going to be 7/10. And then 89 pennies, so if you are from America or Canada, you will probably know that a penny, 1 penny is a hundredth of a dollar. Basically, there's 100 pennies in $1. So if we have 89, then we have 89 hundredths. Okay, so these are our different fractions to represent our different amounts, and all we're going to do now is we're going to add up these fractions. So 13 quarters plus 7/10 plus 89 hundredths. So what we need to do now is make a common denominator, and a common denominator for these is going to be 100. So if we do the numerator and denominator of this times 25, that'll give us a denominator of 100. And then for this one, 10 times 10 is 100, so we'll also multiply the numerator by 10. All right, so we've got 13 times 25, which gives us 325. So we have 325 over 100, plus 7 times 10 is 70 over 100, plus 89 over 100. All right, so 325 plus 70 is 395. And then we are adding 89 over 100. 395 plus 89 is 484 over 100. And since we're dividing by 100, this is just moving the decimal over twice. We get 4.84 or $4.84. All right, so if you want some idea of how to do these kind of financial questions, check out episode 31 of the series where we do that application. So question 5 says, use number line compressing to demonstrate how one could plot 7/3 on the number line. Okay, so recall, number line compressing was just division, right? And so if I'm going to go from 0 to 7 on my number line here. So what we can do is if we divide this number line by 3, we're compressing it by 3, and we always fix 0. And then what we do is we make all the distances between these points to be basically 1/3 smaller. We're making these distances 1/3 in size. So that means if we kind of compress all this down, we're going to get 3 right here. And then we've got 1 and 2. And then 4, 5, and then 6, 7, 8, 9, and so on and so forth. But essentially what we've done is we've taken this number line here, an extra copy of it, and we've compressed it down. And it makes sense, right? 3 lines up with 1 since 3 divided by 3 is 1. 6 lines up with 2 since 6 divided by 3 is 2. But what we also did is we showed that this is basically used to show that fractions are just division, right? Because what we can do is 7 divided by 3, if we think of that as 7/3, well, where does that line up with? That lines up right here on the number line. So that gives us a way to basically plot where 7/3 is, right? 7 divided by 3 is 7/3, and that is going to be where this compressed number line matches 7 up with on the original number line. And if you want some more context on that one, check out episode 24 of the series. So part A says a quarter pounder has less meat than a third pounder burger. So all we need to do here is we compare a quarter with a third, and well, we can see that they have the same numerator, so it's all about comparing the denominator. 3 is a smaller denominator, so 1/3 is a bigger fraction. So it is true then that a quarter pounder has less meat because it's a smaller fraction. So if you're kind of interested in why specifically I'm talking about burgers, check out episode 33 of the series where it gives a real life application to how people got this confused. Part B says I have two fractions. The first fraction has a smaller denominator, so it must be the larger fraction. So off the bat, you might think, well, yeah, that's true, right? We just use an example of that, right? Smaller denominator means we are splitting up into smaller pieces, so it's got to be the larger fraction. So that is true. However, this doesn't say anything about the numerators of those fractions being the same. For example, let's say I have a third, and then I have the fraction 5001 over 4. So despite this having the smaller denominator, we clearly see this is not the bigger fraction, right? 5001 over 4 is the bigger fraction because it has a way bigger numerator than that 1/3, right? This is between 0 and 1, but this is much bigger than 1. Right? So basically the point is despite knowing information about the denominators, if we don't have the same numerator, we can't use that denominator method to say that the smaller denominator means the bigger fraction. Because we weren't given any information about the numerators, we cannot make any definite claims. So that's why the question had to be false. All right, moving on to part C, it says 1/3 of the following fraction is white. So we see that this rectangle is split up into 3 pieces, and one of them is white. So you might think, well, one of the 3 pieces is white, we're good to go. However, remember, fractions are saying these 3 pieces are equal in size, right? They're equally represented. But this white sliver is much smaller than these blue pieces, right? So we cannot actually say that 1/3 of the fraction is white. So this is false, since the white piece is smaller. All right, going on to part D here. It says in Minecraft, if a player stands on 17 layers of snow, which is a height of 1/8 per layer, they will be at a height of 15/8. Okay, so recall with snow, it's always off by 1. A full block will be 8/8, right? Or basically 8 snow layers. So one full block is at 8 snow layers. So then two full blocks will be 8 plus 8, or 16 snow layers. And then we're just putting one extra layer on top. So this will be 17 layers right here. Now, up to the 16 layers, it's going to be basically one less always. That was just a property with snow. So this height here would be 15 out of 8. So one of the snow layers is always visual. So when you stand on it, you're sunk in a little bit. So your actual height will be at 15/8. However, we saw that there was a little bug in the game where you added an extra layer on top of a full block like this, and it still calculates the height underneath as 15/8, and it doesn't change it. So D is a true statement. And lastly, it says the proportion of numbers divisible by 3 on a 6-sided die is 1/3. All right, so on a 6-sided die, the options we have are 1, 2, 3, 4, 5, and 6. And we're looking for the numbers that are divisible by 3. So 3 is divisible by 3, and 6 is divisible by 3. 1, 2, 4, and 5 are not. So the proportion of numbers divisible by 3 on this 6-sided die, that's the number of numbers that are divisible by 3, so that's 2, out of the total amount, which is 6, so 2 out of 6. But this can be simplified to 1/3, so E is a true statement. All right. Question 7 says which fraction is larger? So we've got 1,000,000,007 over 1,000,000,006 versus 5,000,000,007 over 5,000,000,006. So we could try and make a common numerator or denominator, but that isn't going to be a very effective method. But one method that we kind of saw, one little trick with these is, well, these are kind of the same kind of form where the numerator is just one bigger than the denominator, right? 1,000,007 is one bigger than 1,000,006. 5,000,007 is one bigger than 5,000,006. So maybe we can use that somehow. And indeed we can, because what we can do is we can convert these into mixed numbers. 1,000,007 over 1,000,006. Since this is one larger than basically 1,000,006 over 1,000,006, this is essentially just 1 plus that extra 1 over 1,000,006. Right? So 1 and 1 over 1,000,006, because if we made this into a improper fraction, we'd basically be doing 1 times 1,000,006 plus 1, which is 1,000,007, right? And then similarly, we can say, okay, 5,000,007 over 5,000,006, that equals 1 and 1 over 5,000,006. So now since both of these have a 1, it's just a matter of us comparing 1 over 1,000,006 to 1 over 5,000,006. And since they actually have the same numerator now, it's really easy to do that. Bigger denominator, smaller fraction. So that means this right here is going to be the larger one. So the second part of the question says, in general, given two fractions where the numerator is one larger than the denominator for both. So one example is the pair above, right? So the numerator is one bigger than the denominator. Which of the two fractions will be the larger one? So it's saying if I have two fractions of this form, how can I figure out which is the bigger one? So for example, if I have 11/10 versus 101 over 100, right? The numerator is one bigger than the denominator. Or another example, 3,001 over 3,000 versus 1,999 over 1,998, right? The numerator is just one bigger than the denominator. Which of the two fractions is going to be the bigger one? And for simplicity, let's just keep these positive. So I should have said that in the question. All right, so it's saying, given any of these, basically we can use this trick, right? This can become 1 and 1/10 versus 1 and 100th, or 1 and 3,000ths versus 1 and 1,998th. All right, we're just using this trick every single time. So instead of doing that, can't we just figure out a general way of saying it? Well, since we're using this trick, we end up doing basically 1 and 1 over the denominator, right? This is 1 and 1 over 10, 1 and 1 over 100, 1 and 1 over 3,000, 1 over 1,998. So because of that, what it ends up boiling down to is which one has the smaller denominator, right? This one was larger because this had the smaller denominator, which made it a bigger fraction. So in general then, given two of these fractions, since we're going to be using this trick every single time because they're of this form where it's one larger in the numerator than the denominator, we can just say whichever fraction has the smaller denominator. Right, so whichever fraction has the smaller denominator, since they're both going to be expressed as 1 and 1 over the denominator anyways. So if you found that one to be a little tricky, check out episode 32 of this series. Specifically, the exercise videos, we do a problem that's pretty similar to this. All right, we're down to our final three problems here. So this one says, consider the fractions 1/16, 2/16, 3/16, 4/16, and so on. So all fractions with denominator 16th. And it says only fractions with an even numerator can be simplified further. Why is that the case? So for example, 2/16, that can be simplified into an eighth, right? We just divide those both by 2. 4/16, that can be simplified into a quarter, dividing both the numerator and denominator by 4. But 1/16 and 3/16 cannot be simplified. So the question is asking, why is it only for even numerators that we actually get a fraction that can be simplified? Well, the reason is what does it mean to simplify a fraction? It's essentially us finding a common factor in the numerator and denominator and removing it, right? Dividing by that. So in this case, our common factor was 2. In this case, our common factor was 4. So to get the real answer to this, let's look at the prime factorization of 16, because that'll tell us all about its factors. So 16's prime factorization is 2 times 2 times 2 times 2, right? 2's are all primes. But what do we see? We see we have only 2's. That means 16 will only have a common factor with something if that also has a 2 in its prime factorization. And what numbers have 2's in their prime factorization? Even numbers, right? So only even numerators will simplify a fraction with the denominator of 16. All right, and odd numbers, again, they have no 2 in their prime factorization, so it's not going to simplify. It's as simple as that. And if you want to know more about this, check out episode 23 of the series. All right, question 9 asks, what are the conditions we must place on the numerator of a fraction with a denominator of 21 for that fraction to already be simplified? Okay, so we have a fraction and its denominator is 21, and we basically want to figure out a numerator here, not 0, that's just a circle, but we want to figure out a numerator right there where it's already going to be simplified. Basically, that fraction in simplified form will be out of 21. We're not changing it any further. So to already be simplified means it's not going to have any common factors with 21. So let's look at the prime factorization of 21, which is going to be 3 times 7. So basically, in order for the numerator to not simplify with the denominator, it can't have 3 or 7 in its prime factorization. Otherwise, it has a common factor, which means it can be simplified further. So the numerator cannot have a 3 or 7 in its prime factorization. All right, and that is also covered in episode 23 of the series. So part B says, what are the conditions we must place on a number with 2 decimal places to ensure that the number, when converted into a fraction, is going to have a single-digit denominator? Okay, so for example, if we take a decimal such as 0.31, we know that we can convert that into a fraction by taking the number without the decimal, so 31, and in this case the decimal is slid over twice, so we're dividing by 100. So every 2 decimal place number, we can essentially put it into a fraction out of 100. But some of those, for example, if we did 0.22, those can be simplified, right? So in this case, we can simplify it down into 11 over 50. But this is saying we want to find a condition on these 2 decimal places here, such that when we convert it into a fraction, we actually simplify all the way down into a single-digit denominator. Okay, so for 100 to simplify down into a single-digit denominator, first of all, let's just look at its prime factorization, which we did earlier in the video, which is 2 times 2 times 5 times 5. So from this, we can form all the factors of 100, and the question is what factors of 100 are single-digit? So 2 is single-digit, 2 times 2 is 4 is a single-digit, and then 5 is also a single-digit. Any other factor of 100 is going to be more than 1 digit. For example, 2 times 5, which is 10, is a factor of 100, but that's 2 digits big, so that's too big. So these are all of the possible factors of 100 that are a single digit. Why do we care about this? Because when 100 is simplified, it's going to get simplified down into one of its factors, right? So 100 can be simplified down into 2 by dividing by 50. 100 can be simplified down into 4 by dividing by 25, and 100 can be simplified down into 5 by dividing by 20. So essentially, we need to figure out a decimal that'll give us a numerator that will allow us to divide 100 by either 50, 25, or 20, because that's going to give us a single-digit denominator. So in order for this to simplify as such, we basically need to get a numerator that's divisible by 50, 25, or 20. So we need a numerator that's divisible by 50, 25, or by 20. Okay, so let's look at some examples. So for example, if I gave you the fraction of 0.40, okay, 40 is divisible by 20, so then 0.40 written as 40 over 100. Simplifying that, dividing both by 20, we get basically 2/5, right? But this is kind of cheating in the sense that, is this really a 2 decimal place decimal? Because the second decimal place is a 0, right? So anything that's a multiple of 20, right, that's just going to have a 0 there. So we don't necessarily need the 20 because any of those decimals can be just written as a single decimal place number, right? Similarly with the 50, well, we could do 0.50, right? And say, okay, that's 50 over 100, which is a half. Great, we get our single digit denominator. But again, 0.50 is just the same as 0.5. So again, do we really need to say it's divisible by 50? I mean, it's true, but again, it's not really a 2 decimal place number in the sense that this is an unnecessary digit we're putting there. But the 25, that's where it actually gets good, because the 25, right, for example, 0.75, that's something where both of these are non-zero, right? They're both meaningful digits. So this can be written as 75 over 100, Dividing both by 25, we get 3/4. That has a single digit denominator. So the 25 is like the best one in the sense that it's actually a necessary 2 decimal place number, whereas any decimal that is basically divisible by 20 or 50, that ends in a 0 anyways, so it's not really going to be a 2 decimal place number in the sense that that second decimal place is always a 0. But in any case, any of these 2 decimals that are divisible by 20, 50, or 25 will give us a simplified fraction with a numerator that is 1 digit. So that's a pretty tricky question, but it's a pretty interesting one. And let's move on to the final challenger for today. So tragically, I ripped this a little bit, but I'm not going to waste an entire piece of paper to print this off again. So forgive the little tear there. So this says, prove that a whole number plus a simplified fraction will always be simplified. What implication does this have for mixed numbers? Okay, so we've got a whole number, right? So let's say something like 1, to keep it simple, plus a simplified fraction, let's say a half, so 1 plus a half. And it's saying, okay, that will always be simplified. Okay, so let's see. If we do 1 plus a half, that's 1 over 1 plus 1 over 2, and a common denominator for this is 2, right? So this is going to be essentially 2 over 2 plus 1 over 2, which is 3 over 2. So basically what it's saying is that when we do this process, we're not going to have to simplify it any further. It's still going to be a fraction out of 2. And so similarly, if I did something like 3 plus 3 over 7, this can be basically converted like we normally do with mixed numbers into improper fractions. So 3 times 7 is 21 plus 3 is 24 over 7. And yep, sure enough, that can't be simplified. But how do we know this is true for every single instance? So this is a little bit tricky to show, but it is still something that we can do. So the first key part is to note that when we're doing a whole number plus a simplified fraction, basically we are doing the whole number and we're multiplying it by the denominator, right? Doing the whole number times the denominator. And then we are adding the numerator. And then after all of that, we divide by the denominator, right? That was kind of our method of basically adding a whole number to the fraction, or basically converting the mixed number into an improper fraction, right? Adding a whole number with a fraction is the same as basically converting a mixed number into an improper fraction. We talked about that in the video of converting mixed numbers into improper fractions. So we have a whole number, right? So like the 3 times the denominator, right? Times the 7 plus the numerator of 3, and then over the original denominator. Now, the key thing here is to note that the whole number times the denominator, what this is going to do is it's going to give us a multiple of the denominator, right? If we take a whole number and we multiply it by something, well, we get a multiple of it, right? So a whole number times the denominator gives us a multiple of the denominator. 3 times 7 is 21. 21 is a multiple of 7, right? So we get a multiple of the denominator, and multiples are divisible, right? So without this numerator, a multiple of the denominator, this would be divisible by the denominator, right? If we didn't add a 3 here, 3 times 7 is 21. That's divisible by 7. However, when we add this numerator in, it's not going to be divisible by 7 anymore, right? Because the numerator we're adding, it's simplified. And since it's simplified, this 3 cannot be 7, right? This numerator over the denominator is simplified, so this numerator cannot be the denominator, nor can it be a multiple of the denominator. So cannot be a multiple of the denominator. Why is that? Well, our numerator over our denominator, I'm just going to write that as num over dem, or den. Our numerator or denominator is simplified, right? It's simplified, so that means the numerator is coprime with the denominator. So since this is coprime with that, it can't be a multiple of it. Otherwise, they share a common factor, right? And they're not coprime, and it's not simplified. So the numerator cannot be a multiple of the denominator. So if we take a multiple of the denominator and we add it with something that's not a multiple of the denominator, this whole thing won't be a multiple of the denominator. So this whole thing here, not a multiple of the denominator. So what that does then is it tells us in a case like 3 plus 3 over 7, We're getting a multiple of the denominator by doing 3 times 7 is 21. Then we're adding 3. That's not adding another 7 or another 14 or 21. It's not adding multiple of 7. So it takes us to something that's not going to be divisible by 7, right? So then we basically guarantee a numerator that's not divisible by the denominator. So that's part of our reasoning. But that's not the entire reasoning. Because what if I had something like, let's say 3 plus a 12? Okay, so we do 3 times 12, which is 36, plus 1 is 37 over 12. And we see, okay, yeah, 37, not a multiple of the denominator. Great. But the thing is, to simplify a fraction, we don't need the numerator to be a multiple of the denominator. We just need a common factor. For example, 4 over 6. 4 is not a multiple of 6, but this can be simplified because they have a common factor of 3. So we also need to keep in mind, okay, what about the common factors? So what we can do here is we can say, okay, this denominator has a prime factorization, right? So denominator has a prime factorization. Let's say it's, prime number 1 times prime number 2, and so on and so forth, right? Maybe there's 10 different prime numbers that make up our denominator. So this is pretty tricky here, but let's just try and pay attention for a second. So a denominator is a prime number times another prime number, and we've got a bunch of prime factors, right? But if we do a whole number times the denominator, we're essentially doing that whole number times all of these prime factors, right? So in this situation here, right, when we did 3 times 12, that's the same thing as doing 3 times all of 12's prime factors, which is 2 times 2 times 3, right? So essentially, what we have up here isn't just a multiple of the denominator, but it's a multiple of any one of the denominator's prime factors, right? Because here, okay, if we do 3 times 12, that's going to be 3 times 2 times 3 times 2. It's a multiple of this 2. Or 3 times 2 times 2 times this 3. It's a multiple of this 3. So you see how this product here will give us a multiple of any one of the prime factors. So not only are we a multiple of the denominator, we're a multiple of all of the denominator's prime factors. And now we're going to do something very similar to our previous reasoning. Since the numerator or denominator is simplified, the numerator has no common factors with the denominator. So none of the denominator's prime factors are in the numerator's prime factorization, right? That's what it means to be coprime. So since it's simplified, the numerator, or num, has none of the denominator's prime factors, which means the numerator can't be a multiple of the denominator or its prime factors. And some of you may see where I'm going with this. A whole number times the denominator, if that's a multiple of the denominator's prime factors, and we add something that's not a multiple to its prime factors, we are not going to get a multiple, right? If I have 6, that's a multiple of 3. If I had something that's not a multiple of 3, well, we're not going to get a multiple of 3, right? Because this is, okay, we do 3 plus 3 to get 6. Then the next multiple will be adding another 3, right? We're not adding another multiple of 3, so we don't get another multiple of 3 out of it. So similarly, our numerator is the whole number times the denominator. That's a multiple of the denominator's prime factors. We're adding something that's not a multiple, so this whole numerator will not be a multiple of any of the denominator's prime factors, which means that this is a coprime numerator and denominator. This is not simplifiable. So that was a very difficult problem, okay? At this stage, this is very hard, I'll admit it, but it is worth your time watching this over again, trying to really understand this, because if you can understand this, you're more than equipped to be doing a lot of difficult algebra. This is a hard problem, so if you didn't get this, don't feel bad whatsoever. But yeah, so I guess let's also look at the last part here. What implication does this have for mixed numbers? We saw that this is how we can convert a mixed number into an improper fraction if we do something like 3 3/7, 24 over 7. Basically, the idea with mixed numbers is that if we get a fraction out of 7 or out of whatever denominator, when we convert it into an improper fraction, we will get the exact same denominator as well. So the implication for mixed numbers is that it will have the same denominator as it does for its improper fraction counterpart when they're both simplified. And question 10, if you want some kind of context for this problem, please check out episode 28 of the series. This is way harder than anything we did in there. Again, if you really struggled with this, that's all right. Try and watch it several times, ask some questions in the comments. Give it a good effort to try this problem out. But again, don't feel bad if you don't get it, because it's tough, I'll admit. All right, well, that's going to do it for today. I hope you found this episode useful. I hope that you are feeling good about fractions now, even after that monster that was number 10. And I'm looking forward to this next kind of section of videos, and I hope you are too. But let me know how you did on this checkpoint in the comments. I'd be really interested to know what you thought of the problems. But until the next video, you have a good one, you stay groovy, and I'll see you then.